All right. Can you all hear me? So welcome everyone for our first session, which is our best paper candidates. We have 3 best paper candidates. And let me first introduce Birkan Denizer. He's a 4th year PhD student from Kiel University in Germany. And he's going to talk about his work on capacity-aware uplink bandwidth prediction for cellular networks. Please welcome him.
Thank you for the nice introduction. My name is Birkan, and today we will be talking about uplink predictions. But why do we even need uplink predictions, right? So in the recent years, we have increasing number of autonomous and remotely controlled devices. For example, they can be cars, they can be ferries, they can be drones, or maybe some fancy-looking next-generation trains. And then, most of the time, these are focused on using the uplink part of the network connection because we want to send maybe video traffic, maybe we want to send some data for the control because we want to do like remote monitoring or remote control where the uplink is the most important part of the network. And of course, in the big picture, when we look at the network, there would be maybe 2 different ways of looking at these parts. And we will start building this plot on the bottom over time. But let's start with the reactive approach. In the reactive approach, in the reactive control loop, for example, we start by sending some data, and at some point we start sensing what's going on in the network. This could be some packet loss, this could be maybe some latency spike, and at some point we detect what's happening in the network. This could be like a rule-based system where you're just detecting that there is like some amount of packet loss, or it could be some fluctuations in the RTT. And of course, at some point you do some sort of adjustment of the traffic. For example, maybe it's adjusting the bit rate, or it could be as simple as switching to a different link that has better characteristics. And of course, when we look at our plots, maybe now the picture looks a bit different because we started sending some traffic. And at some point, we hit the limits of the capacity, and then we need to react because we are sending too much traffic. And then this will repeat, as the prior speaker mentioned before, this will repeat over the connection lifetime, but we want to do something better. On the right side, we have the proactive control loop. Again, we send some traffic, but this time before we send some traffic, we start by sensing what's happening on the channel. For example, this could be sensing what's happening on the signal strength. It could be changes in the band configuration. And then eventually using the features that we have, which I will go later in detail, we are going to make some predictions. For example, this could be predicting the upcoming network handovers, or it could be predicting the upcoming bandwidth. And then we are going to do some acting, which is, again, similar to before, adjusting the bit rate and maybe switching the link, but we will do this in time proactively. And when we look at the bottom part, now maybe our proactive sending rate will look slightly different because we know that with the changes in the network, we can stay below the capacity, and then we can avoid this overuse of the capacity. And of course, this is easier said than done. Of course, we have some challenges. The first challenge is the network handovers in the network. And then, for example, due to mobility, for example, cars or ferries, when they are moving from one base station to the next one, we have changing signal strength most of the time, or changing band information. And for example, the first effect is that around these changes, we see reduced bandwidth. So this is reducing the total amount of bandwidth due to maybe signal changes. At the same time, we most of the time see also increased latency because with the reduced link capacity, maybe if your algorithm is not adapting in time, you are still trying to send the same amount of data, which is coming closer to the congestion. And on the third point is that if we want to train some machine learning model at some point, we need 5G data sets with handover information. But when we look at the literature, it's hard to find 5G standalone data sets that have handover information inside. On the right side, assuming that we have a prediction model, we make some predictions. And of course, our prediction model usually makes an error. When we look at the error itself on the bottom right side, we see that, of course, our model is making predictions sometimes in the over-prediction region, which means you're basically sending more traffic than you can actually achieve. And of course, sometimes it's just doing under-prediction, which is less than ideal, but there is not like significant damages done. You're just like not utilizing the network fully. But when we look at this in the big picture, we see that over-predictions hurt the network more than under-predictions, because over-predictions most likely will result in packet loss. It will be resulting in retransmission, and this is something that we don't want to have in the big picture. And of course, for training machine learning models, most of the time we rely on loss functions. And in this case, we don't want to have a symmetric loss function because we don't want them to be equal in the amount of damage they do. So we will look into how we can actually improve this in a few slides. Just to give some context of what we are doing compared to prior work, of course, there are some prior work from different conferences in the last 4 to 5 years. And some of them, or all of them actually, can do uplink bandwidth prediction. But most of them, they don't look at the effects of network handovers. And even some of them, they don't think about the loss function at all. And there is only one prior work that is using asymmetric loss function. But this is very static, and it's not actually learnable. It doesn't change its behavior depending on what's going on in the network trace, for example. And moreover, some of them also use specific features, input features. For example, some of them are using transmission power, which is a very low-level feature that is not available as a metric in most of the APIs, for example, in Android or different platforms. But in our approach, we are using just the common features that you can find in most of the APIs. Let's go to the contributions of our paper. First, we designed CapAware. It's an uplink bandwidth prediction architecture with integrated handover prediction model as well as our custom loss function. We call our custom loss function an asymmetric relative utilization loss function, which I will go in detail in the next slides. We collect a new 5G standalone dataset with commonly accessible metrics. And it also includes the network handover information, which is very crucial for us to train our models. And of course, we evaluate our approach against state-of-the-art baselines, which I will detail in the baseline section later on. And with our approach, we achieved 93% F1 score with our handover prediction model, which is higher than before. And we achieved 34% higher network efficiency compared to state-of-the-art models, which I will detail later in our metrics. Okay, let's start with our design. Of course, I mentioned briefly at the beginning that we are relying on some features, but what are these features? For example, on the top, we have features coming from the signal strength, maybe traditional features that you can find, signal-to-noise ratio. This could be channel quality indicator. This could be RSRP. But at the same time, we are also relying on previous handover information as an input, as well as band information in one-hot encoded way. If you think about the band information for a second, this could be the N28 band that you are using, maybe N3 or N78. So this could be low band or mid band. And just relying on the channel width as like 10 megahertz, 25 megahertz, or 80 megahertz is not enough, because some of these channels have FDD or like frequency division duplex configuration, and some of them have configurations, which is not enough to just look at the bandwidth, channel bandwidth. So we are using one-hot encoded way, so we can categorize them in a better way. And of course, using some of these features, we predict upcoming network handovers with our model, and then our prediction model outputs handover prediction for the next second. And then, using most of the features that we show, we put them into, or we use them as input for our bandwidth prediction model, as well as into our custom loss function. So this part is also important, that the handover information is not just going to the model, but it also goes to the custom loss function during training, so we can train our model in a better way than before. And these three boxes, handover prediction, loss function, as well as the bandwidth prediction, is like an outlook for what we are going to discuss in next steps. Let's start with the handover prediction part. We model this as a binary classification problem. So this could be viewed as yes or no. And we are mainly relying on signal strength metrics, the ones that I mentioned before. And, but we have the option of using GPS, for example, localization features. If you think about the context of a vehicle, most of the time a vehicle knows its location. It could be, it knows its location, but we are not just using latitude and longitude, but we are actually using the speed, which I will briefly mention later on. And in our model, we don't use any custom data points. So there are other papers that claim that they can do high accuracy classification by using really like low-level features like radio resource control messages. But this is not a very portable way of doing this. You can't just do this on a smartphone without like rooting the device or going into like lower layers. Just to briefly show what we are doing, we have the main features, the core features coming into our model. But we can also train our model with the GPS if possible. So this changes based on the availability of the data. Maybe if you're on a phone, you want to save some power. You don't want to turn on the GPS all the time. This could be energy saving. And at the end, we don't just actually predict yes or no, but we actually look at the probability of handover. Because based on this handover probability, we will actually adjust our bit rate. Because if we know, okay, the probability of handover is high, then we know that, okay, it's better to maybe under-predict, so we can adjust our bitrate even lower. But when the probability of handover is low, then we can actually just send like higher bitrate data. Next, let's talk about our custom loss function. But just to set the context, on the left, we have one of the most common loss functions. This is mean squared error. I think most of you are hopefully are aware with this. When we look at the x-axis, so on the x-axis we have the bandwidth error, which is like minus or plus, and on the y-axis we have the loss. So in this context, when we think about this, if your model makes 1 megabit plus error or minus 1 megabit error, they give the same loss. But as I mentioned at the beginning, having a plus loss, like over prediction, hurts more than under prediction, because this will basically result in packet loss. Just to just to give like a better perspective, I'm now changing the x-axis on the first plot from absolute error. Now we are going to do relative utilization. What does relative utilization mean? For example, if you're on a connection that has 100 megabit capacity and you're sending 100 megabits, this would be 100% or 1.0 in this context. And when we now compare to mean square error, in our asymmetric relative utilization loss function, now we define 3 regions, not just 2. And the first thing that you can see is that on the right side, we have a much higher increasing penalty. So if we actually look at the ranges that we defined, we have a quadratic penalty on the over-prediction region because we don't want to just do over-predictions all the time. We want to avoid these bursty, over-prediction errors. But of course, we also don't want to just utilize network with the 50% utilization. So what we did is we created this middle region where we call it mild under-prediction. So this is more like the sweet spot of the network. Let's say this would be like 90 to 100% network utilization. You also don't want to be really close to the like 100% because this will also increase the congestion. So what we did is we have a smaller linear penalty in the middle and increasing medium linear penalty when we have lower than 90% utilization. But the nice thing is all of them are configurable. So this is more like a hyperparameter optimization when we train our model, which I will detail later as well. And one of the advantages, as I mentioned at the beginning, is that we are also using this handover probability when we are training our model. So the model knows how to get better, how to understand its input better without this, compared to what it could do without this information. And then just to round up the bandwidth part as well, now we have the predicted handover information coming in rather than just 0 and 1, like handover or no handover into our model, as well as our custom loss function. And now at some point, after some milliseconds, then we get an output. For example, it could be something as 73 megabits of predicted bandwidth. One thing that is missing from these inputs is why there is no past bandwidth. Like, this is something like a good question to ask, I would say, because we think that just using the past bandwidth is unreliable. For example, you might be on a connection, maybe a 5G connection, you can achieve like 100 megabits of capacity, but you're only sending 2 megabits of video traffic. What the model will most likely do is you're just going to predict maybe 3 megabits or 4 megabits. So unless you congest the network with incoming input traffic, using or relying the past bandwidth as an input is not generalizable way in our opinion, so we are not using this as an input. Okay, now let's talk about the evaluation. First, I will go through the baselines and the configuration. As I mentioned at the beginning, we are using 3 different state-of-the-art models. They are offering different model configurations. And on the handover prediction side, we look at one recent paper from ICC that uses a similar architecture to ours, but rather than doing classification, they do a bit of regression way of doing it. And then when we compare our loss function to some of the loss functions that are existing today, we are going to talk about MSE as well as quantile loss, which is a cheap and easy way of doing asymmetric loss function. So in one of the papers, they were using quantile of 0.45. So in this context, we are also going to evaluate against that baseline. Let's talk about the metrics. I think this is quite interesting. Of course, utilization is something that we all want. Like, we want high utilization in our network. We don't want just send at half the utilization. But this is in the context, why do we want high utilization? At some point when, at the beginning, I mentioned that when we are making predictions, at some point the predictions get over predictions or under predictions. So increasing the utilization has some side effects. So in the first parameter that we are going to discuss is area of violation. So this is the total amount of area that you are sending with over prediction. So this is basically the area that is resulted in packet loss. This could be considered as the area under the curve. Imagine a line that your prediction is above the capacity, and then this will result in an area. But when you think about this, there is one big problem. So having a bursty short error, like 5 megabits of error, as I wrote in the slides, for 1 second is equal to 1 megabit of error for 5 seconds. So they give the same area, but they have much different characteristics. So this, when we look at the area of violation, we cannot understand whether our error makes a bursty error or if it's just like a small error over a long time. So what we came up with is volume of violation. So instead of area under the curve, this is somewhat of a volume under the curve, so to speak. And this way we can actually see if our prediction error is making too much errors. And this is, in this context, lower is better. And then combining utilization with volume of violation, we came up with efficiency index. This is a way of looking at how much utilization we have compared to error that we make. So we want high network utilization, but we want low amount of errors, low amount of volume of violation. This is a normalized value between 0 and 1. You can find more details in the paper. It's just giving a comparable result among different models. And for just sake of transparency, we are not going to use area of violation. As I mentioned, it's less of a metric compared to volume of violation. We did a measurement campaign in Kiel, Germany, with our autonomous ferry MS WaveWeb, using 5G routers that support 3GPP release 16. And this is based on our Fjord 5G paper. So it's using a similar architecture, but with the newer release 16 routers. It's on a public 5G standalone network, and it's 6 months of data collection. And in our paper, actually, we are not just relying on our Fjord 5G paper, or data set, but we are also relying on Uplink net data set, which is coming from Asia Pacific region, from Thailand and Japan, as far as I remember. But due to time limits, I will mostly focus on our data sets for our results. But you can also find results for the Uplink net in the paper itself. Let's start with the evaluation of our handover prediction model. Just to give some labels, so on the x-axis we have the number of the features that we are using to make predictions, And on the y-axis, we have the percentage of accuracy, F1 score, recall, and precision. When we start looking at the prior work from Lima et al., they are using only RSRP as the input feature, and then they can achieve 87% F1 score. But when we compare to CapAware, our own handover prediction model, we can already achieve better scores just by using RSRP. And when we increase the number of features that we are using, especially when we also add GPS, we can achieve 93.2% F1 score. This is much higher compared to prior work. And one thing that is interesting to see is that we get mixed results with RSRQ. So in our final model, we decided not to use this as an input feature. And then one thing that is also interesting to see is that GPS, as I mentioned before, is depending on the device that you're using. If you want to deploy this model on an Android phone, for example, you can disable the GPS and maybe not use it all the time because it's going to drain your battery. But if you're in a vehicle context, the vehicle knows its position most of the time, it's a free 1% uplift almost. Now we are going to compare our loss function against some of the baselines. So on the x-axis, we have basically the error. So this is the volume of violation. And on the y-axis, we have the network utilization. We have two static baselines. So this plus is basically the quantile loss. This is the lower bound, so to speak. And then we have the mean square error on this side. And most of the time, we think that we will be in a range between these points. And of course, the further top left is the direction where we want to go. We want high network utilization and low amount of errors. When we look at our loss without handover information, this is the circular points. We have many configurations, as I mentioned before. This is based on hyperparameter search. So all these linear penalties, they were all configurable. And then we found out which configurations were the best based on our hyperparameter search. And when we look at the results, we actually get even higher network efficiency when we use handover information. So compared to the quantile loss, some of the cheap way of doing the under prediction, we get 2% higher network utilization at almost the same error rate, which is nice to see, in my opinion. And just to round up all the parts of our models, so now we are evaluating our complete model against the other models, and we see that our model is achieving between 10 to 35% higher efficiency index compared to other models. So our model is still performing with a high network utilization, but doing much less errors. And the other models are actually just staying in a low network utilization in this context. You can find more specific details of how we are doing this in the paper itself, or ask me questions later on as well. Just to sum up and conclude, today we talked about uplink bandwidth predictions and its importance for autonomous and remotely controlled vehicles. We talked about our CapAware architecture with its integrated handover prediction model as well as custom loss function. We talked about evaluation of CapAware with 93% F1 score for predicting network handovers and up to 34% higher efficiency index compared to state-of-the-art baselines. It's an open source implementation, is public. You can find it on our GitHub. I think I will add more details later this week, so I have a basic template at the moment. And if you have questions, please reach out to me or ask questions now. Thank you so much.
Thanks a lot, Birkan. Now it's time for questions. I don't want to break glasses.
Thanks for the talk. Just a quick question. You motivated your work by real-time traffic, video traffic, if I got it right.
It could be real-time video traffic, or it could be real-time sensor traffic coming from LiDAR. It could be coming from a millimeter wave. Maybe some of these are processed on the device, on the vehicle, but some of them may be sent to the control center, for example.
Yeah, so you increase the prediction accuracy, if I got it right. But does this improvement has an impact on the application, or doesn't not matter at all? Because you improve it by, let's say, 20% or something. Mm-hmm. does it have an impact on the application, or yeah, because application, especially in multimedia real-time stuff, is kind of not that easily. It's not that easy to show the impact on the application, really.
I think this is a good question. It's just like how do you do A/B testing, right? I think that's the point. Now we are actually deploying this on our Wavelab, our ship. It's running inside like a Docker container on the ship, and then we are testing WebRTC-based video streaming and how it's interacting with this, but I don't have final results that shows we get, I don't know, 5% better quality of experience or something like this. I think that's the next step, obvious next step, combining this approach with maybe media streaming application or maybe some sort of congestion control. There are already prior research that shows predicting bandwidth can be very beneficial for congestion control. So you have one congestion control that is handling maybe a VPN connection, or it could be handling like a single connection. And that will be the next step, but in this work we didn't do this yet.
Okay, so first of all, thank you for your talk. As far as I get, you want to control something in the application layer with metrics you receive from the very low level layers, like the physical layer. But there are several layers in between, and each layer comes with a queue. So normally there are a lot of buffers in our local device, which kind of can handle this. So why are you not looking into the states of your buffer and saying, okay, my buffer fills now up, so probably I have to reduce my data rate of the video stream now?
I think this is also possible. It just requires you to look at multiple applications, multiple buffers, right? So this would be similar to prior talk. It would be like application-informed, application-specific way of looking at this. But the way that we want to use this in our Ferry project is that we have one big VPN that is managing what's going on in each link. And then if you know the capacity of each link, then you can adjust what's going on in the big picture rather than trying to target what's happening in each application. I think, we want to have a global view rather than just one single point of view, I would say. Does that answer your question? Or?
Yeah, not really, but I think we have.
Yeah, you can take it offline. Any more questions? If not, Niels wants to have another question.
Okay, yeah, just another question. You know, bandwidth prediction, right, has been around even before the AI area. So, and in the old days, you were looking at positions and tried to estimate where a user will go, or even you had a train and the train had a train track. So you knew when probably the cell would end, and then you could do a prediction. Have you compared your work to this old work, I would say, or have you considered using some kind of a priori knowledge like cell ranges, cellular ranges in combination with your AI modeling?
So in this work, we didn't compare against statistical approaches, but in my prior work from last year's LCN, in that slide, I had like some statistical baselines where I showed like some of the statistical baselines were better than predictive models. So I'm aware of this, and then it depends on the prediction range. So if we are making predictions for a couple of seconds, like a predictive model is usually performing better, but when we are actually looking at prediction ranges of 5 to 10 seconds, maybe a statistical model is already performing better, which means that our prediction model is not doing its job in a good way. But on the point of location, I think this is also interesting, but then you require like domain-specific information. If I do like my prediction model in Kiel and I want to do it on Osnabrück, then maybe it's not that applicable. That's why in the handover prediction part, we are not using location, but GPS speed. Like if you know that you're not moving, maybe it's a better signal than just where you are, I think. So it's more generalizable in the big picture. But I know, yes, thank you.
All right, thanks everyone then. Given the time, I would like to move on to the next presentation. And let's thank Birkan again.